Hello guys, welcome to my first paper reading video. Today I'm going to talk about a paper that was published in the Conference of Robot Learning in the workshop last year. It is titled as Language Models as Zero-Shot Trajectory Generators. Whether large language models could be directly used to solve some practical problems, such as the robot problems, is always an open question since the release of ChatGPT. So in this paper, the author investigate if a large language model, especially the GPT-4, could be directly used to predict a dense sequence of end-effector poses for the robot arm in a real robot platform, without any requirements for the in-context examples, but only with two pre-trained vision models. They conduct experiments on 26 real-world language-based tasks, and the experiment results well demonstrate that GPT-4 has the capability to be applied to a real robot. So let's first look at the contributions in this paper. In this paper, the authors demonstrate that the GPT-4 has the zero-shot capability to be applied in a robot manipulator by outputting a dense sequence of end-effector poses without any requirements for the in-context examples. They also demonstrate that large language model has the success detection ability and could subsequently replan an alternative trajectory for the robot to execute. In this paper, the authors also investigate what techniques and prompts that lead to the emergence of these capabilities, which is very instructive for the following research. Before we get started, let's first look at a comparison of the investigation in this paper with other state-of-the-art methods that combines large language models to the robotic problems. I think the biggest difference lies in that the investigation in this paper do not require any in-context examples. They do not require any robotic-specific training data, which is zero-shot manner to output the trajectories for the robot. And compared to code as policies or ChatGPT for robotics, it does not need any predefined primitives, which is a collection of pre-trained skills. Well, let's look at the overall pipeline in this paper. So I want to introduce the pipeline in this paper with their real-world experiment setup. In this paper, the authors use two real-sense cameras, one mounted on the wrist of the robot and the other fixed on a tripod. The camera that mounted on the wrist of the robot first captures a top-down view of the environment at the beginning and then put the picture into long-SAM vision model. So long-SAM model is a powerful instance segmentation model, and it could utilize the text prompts given by the users to generate masks for specific objects. For example, when you text in the word kiwi, it will give you back the mask of the kiwi along with its bounding box. So in this paper, it utilized the long-SAM to detect the 3D bounding box of the required objects that in the task description. And after getting the bounding box of the required objects, the GPT-4 would generate a dense sequence of trajectories for the robot to execute. Specifically, the large language model would predict a sequence of 4D end-effect poses, 3 dimensions for position and 1 dimension for rotation. Considering it needs to accomplish some pick-and-place tasks, it should also control the gripper of the robot. So after generating a dense sequence of trajectories along with the gripper control commands, the robot arm would execute the specific trajectories in an open loop manner. After the execution, we could get a sequence of video frames during the execution, and we would get the trajectory of the required objects with a pre-trained object tractor model, XMAP. XM is a long-term video object segmentation model that could track the required objects with the mask for a long video. It only needs to put in the tracking object's mask, and then it could autonomously track the mask of the required objects during a long video shot. After getting the mask and the trajectory of the required objects, the GPT-4 would autonomously detect the success status of the task, and if it decides the status of the task is failure, it would go back to the initial stage of the pipeline and detect the objects and generate the trajectories for the robot again until the task is successfully executed. Let's then look at the experiment result. Well, I will skip the prompt development section in this paper, as you could read in detail by yourself. I'd say that it is essential to design a well prompt in order to apply the GPT-4 into a real robot platform. And this paper provides detailed prompt engineering techniques that utilized in order to achieve these tasks. Let's then look at the main experiment result in this paper. Well, the authors investigate 26 manipulation tasks in the real world, and we could observe that the GPT-4 demonstrates surprisingly good zero-shot trajectory generalization abilities in some tasks, while it could also fail in the others. For example, in some fruit manipulation tasks, it could achieve a success rate of 100%. This demonstrates that GPT-4 has a well-vision understanding of the experiment, and it could also capture the right relative positions between the objects in the environment with the help of the 3D bounding box provided by the pre-trained vision models. We also observed that GPT-4 could fail in some specific scenarios or tasks. For example, when there are some personalized word in the task description, for example, the word lonely objects. Human could understand the word in the context of the environment, while it seems that GPT-4 or the vision model has cannot capture the real meaning of the personalized word. And I also observed that some failure cases are often involved with tool manipulations, which requires an understanding of the relative positions of the tool and the objects. A very well understanding, but GPT-4 fails to accomplish these kinds of tasks. And GPT-4 could also fail in some scenarios which requires the interaction with a specific part of the object. For example, pick up the ball or move the pen. It requires the robot to interact with the rim of a ball or the handle of a pen, which could be challenging for the GPT-4 to accomplish such intricate manipulation policies. This demonstrates that there are much more improvement space for the large language models when applied on real-world manipulation tasks, especially for some intricate manipulation policies. Well, let's then look at future investigations made in this paper. The authors first investigate how should the final trajectory be presented with the help of GPT-4. So they compared asking the GPT-4 to output the numerical poses with outputting the trajectory values with the code as shown in figure 7. The experiment result shows that when facing some intricate trajectories, such as drawing a circle or a 5-pointed star, writing the code could improve the success rate from 10% for numerical output to 60%. This suggests that the fundamental property of large language models for control, their understanding of both the code and the mathematical structures can bridge these two modes of thinking. And it also indicates that for some domain-specific output, it would be a better choice to ask the GPT-4 to output the required values with the code instead of directly outputting the numerical values. A similar finding is also observed when the GPT-4 controls the gripper action. So in their result, the experiment demonstrated that large language model could achieve better performance when using explicit functions instead of binary variables in their experiment. The result is shown in figure 8. They compare the success rate when asking the GPT-4 to output the binary value actions directly or output the values with a function. We could say that the success rate improved from around 60% to 70%. Well, the last but also important investigation made in this paper is that the authors investigate the large language models, their detection abilities. Let's recall the overall pipeline in this paper. Do you remember that I mentioned the robot arm execute the trajectories in an open loop manner. So there could be some failures during the execution, or the trajectories could be a wrong trajectory for the robot. So the success detection capability of the large language model would be very important to improve the overall success rate. In Figure 8, they demonstrate that with the success detection ability of large language model and the reprompt trajectories by the large language model, by the GPT-4, the replanning process could lead to a small improvement in the performance. Without planning, the success rate is only 58%, and when equipped with the replanning capability, the task success rate will improve, will be elevated into a success rate of 63%. Okay, that's the overall description of this paper. And I'd like to make some conclusions on my own thoughts on this paper. My first conclusion is that GPT-4 has zero-shot trajectory generalization and success detection ability for real robot platforms. And the pre-trained vision models, such as the long-SAM and the XM utilized in this paper, could empower the large language model significantly. However, I also observed that in this paper, the trajectory is executed in an open loop manner without any visual feedback. This could lead to a low success rate of during the execution. And I also observed that from their investigation, I observed that the code generation is essential for domain-specific output. For example, the trajectories for the robot arm. And if you want to use GPT-4 in your own application, it could be a better choice to let GPT-4 to output the desired values with the code generation instead of output the values directly. Well, so this is my overall thoughts on this paper. Let me know what you think in the comments below. That's all. Thank you.